For 50 years, every textbook, every classroom, every space documentary got Jupiter's size wrong. Not by a little, by miles. NASA just announced that the king of planets, the giant we thought we knew, has been hiding its true shape all along. And here's what makes this difficult to understand. The brightest minds in science, the most sophisticated space agencies on Earth, all missed it for half a century. Stay with me for the next several minutes, because what we're about to uncover isn't just about a planet getting smaller. We're going to explore how this happened, why it took so long to discover, and what it means for everything else we think we know about our solar system. Think about that for a moment. Jupiter, the largest planet circling our sun, the one you learned about in school, the one your children learned about, maybe even your grandchildren. All those numbers, all those facts, they were off. And if Jupiter's measurements were wrong this whole time, this shows how science improves over time. This isn't some minor adjustment, some decimal point moved one place over. We're talking about a planet that turned out to be smaller at its middle and flatter at its top and bottom than anyone calculated. The measurements that shaped our understanding of giant planets, the standards we use to compare distant worlds in other solar systems, they need to be rewritten. NASA's Juno spacecraft circling Jupiter right now kept sending back numbers that didn't match. Scientists checked their instruments. They ran the calculations again and again. The numbers kept coming back the same. Jupiter had been misunderstood. Now, before we go any deeper into this mystery, if you're as fascinated by what we're about to uncover as I am, do me a favor, hit that like button. It tells me you want more stories like this, more journeys into the discoveries that change how we see our universe, and subscribe, because we're going to explore exactly how scientists missed this for so long and what other discoveries space exploration may reveal. Drop a comment too. Tell me what you think we might have gotten wrong about the other planets. I read every single one, and your thoughts always add something valuable to these conversations. Here's what makes this discovery so surprising and interesting. The original measurements of Jupiter came from missions we celebrated. Pioneer 10 and 11, Voyager 1 and 2. These weren't amateur attempts. These were humanity's finest technological achievements in the 1970s. The spacecraft that gave us those measurements traveled farther than any human-made object had ever gone. They sent back images that amazed us. They told us things about Jupiter we'd never known, and we trusted them completely. Why wouldn't we? The data looked solid. The scientists who analysed it were the best in their fields. The measurements became facts. Those facts went into textbooks, and for half a century we built our understanding on that foundation. But Juno arrived with better eyes, more precise instruments, the ability to measure in ways the older missions never could. And what it saw didn't match the old numbers, not even close. And scientists needed to verify their findings carefully. How do you tell the world that something everyone learned, something that seemed so certain, turned out to be wrong? This is where our story really begins. Not with the discovery itself, but with what that discovery reveals about the nature of knowledge, about how we understand the universe, about the difference between what we think we know and what actually is. Because Jupiter didn't change. It's been the same size this whole time, spinning in the same orbit, holding the same mass. What changed was our ability to see it clearly, and that raises something worth thinking about. If our view of Jupiter was blurred for 5 decades, this shows how science improves over time. What else might we measure more accurately in the future? The answer matters more than you might think. Jupiter isn't just another planet, it's a giant that shapes our entire solar system. Its gravity pulls on asteroids, steering them away from Earth or sometimes toward it. It affects the orbits of other planets. Scientists use Jupiter as a measuring stick to understand similar planets circling distant stars. When we talk about finding worlds that might support life, we compare them to Jupiter. So when Jupiter's measurements change, it ripples outward. Models need updating, calculations need correcting, understanding needs rebuilding. But here's what I find most interesting about this whole situation. This wasn't a case of old scientists refusing to accept new ideas. This wasn't stubbornness or pride getting in the way of truth. This was simply the limitation of what we could see back then. The technology of the 1970s did the best it could with what it had. Those measurements weren't wrong because someone made a mistake. They were wrong because we didn't have the tools to measure more carefully. And nobody knew to question them because they seemed reasonable. They fit with what we expected. They made sense within our understanding at the time. So the real question becomes, what are we measuring right now, today, that future technology will reveal was off the whole time? What are we teaching as fact that's really just the best guess our current tools allow? Let me take you back to when we thought we had Jupiter figured out. Jupiter has always been the giant. Even ancient people, looking up at the night sky with nothing but their eyes, could see it shining brighter than almost anything else up there. They named it after their king of gods. They tracked its movement across the heavens. They knew it was important even if they didn't know why. And when telescopes arrived, when we could finally see beyond what our eyes alone could manage, Jupiter became even more magnificent. Bands of colour wrapped around it. A giant red spot, a storm bigger than Earth, spun in its atmosphere. Moons circled it like a miniature solar system. Jupiter wasn't just a planet. It was a world unto itself. But size was harder to pin down. You can see Jupiter, you can watch it move, you can study its light. But measuring exactly how wide it stretches from one side to the other, exactly how tall it stands from top to bottom, that requires more than looking. That requires precision. That requires getting close. And for most of human history, getting close to Jupiter was impossible. Then came the space age. If you're old enough to remember the 1970s, you remember the excitement. We'd landed on the moon. We'd proven humans could leave Earth and come back. And now we were ready to go farther. Much farther. NASA built spacecraft designed to leave Earth's neighbourhood entirely, to visit the giant planets at the far edge of our solar system. Pioneer 10 launched in March of 1972. Pioneer 11 followed a year later. These weren't large machines, about the size of a small car, but they carried humanity's curiosity with them. They were going to Jupiter first, then if they survived, onward to Saturn and beyond. Pioneer 10 reached Jupiter in December of 1973. For the first time, a human-made object got close enough to see details we'd never seen before. It measured Jupiter's magnetic field, which turned out to be enormous, much stronger than anyone expected. It studied the radiation environment, which was harsh enough to damage some of the spacecraft's instruments, and it measured Jupiter's size. Scientists used radio signals and gravitational effects to calculate how wide Jupiter stretched at its equator, and how much shorter it measured from pole to pole. The numbers came back. They seemed solid. They seemed right. Pioneer 11 arrived a year later and confirmed what Pioneer 10 found. Then Voyager 1 and Voyager 2 flew past in 1979, carrying even better instruments, even more sophisticated cameras. They sent back images that filled magazine covers and television screens. Jupiter in detail like never before, swirls in the clouds, lightning in the storms, volcanoes erupting on one of its moons, and more measurements of Jupiter's size, measurements that matched what the pioneers had found. 4 spacecraft, 4 sets of data, all agreeing. That's when the numbers became facts. Those facts went everywhere. They went into NASA's databases. They went into scientific papers. They went into textbooks that students around the world would read for the next 5 decades. If you learned about Jupiter in school any time after 1980, you learned numbers that came from those missions. Your teachers taught them. Your textbooks printed them. Museums displayed them. Planetarium shows used them. They became part of our shared understanding of the solar system. Jupiter's equatorial width, Jupiter's polar height, the amount of flattening at its poles, all of it settled into place as established knowledge, and why wouldn't it? These weren't guesses. These were measurements taken by spacecraft that had travelled hundreds of millions of miles. The scientists analysing the data were experts in orbital mechanics, planetary physics, radio science. They knew what they were doing. The measurements went through peer review. Other scientists checked the work. Everything looked correct. The numbers made sense based on what we knew about how giant planets form, how fast they spin, how their material spreads out. Jupiter spins faster than any other planet in our solar system. A day on Jupiter is only about 10 hours long. That rapid spin should flatten it, pushing material outward at the equator, pulling it inward at the poles. The measurements showed exactly that kind of flattening. Theory matched observation. Everything fit, so nobody questioned it. There was no reason to question it. When later missions flew past Jupiter, Ulysses in the early 90s, Cassini in the 2000s on its way to Saturn, they took their own measurements, but they weren't designed to improve on the Pioneer and Voyager numbers. They had other jobs to do, and their rough measurements generally agreed with what we already knew, so that just reinforced the certainty. Jupiter's size was settled science, locked in, done, except it wasn't. But nobody knew that yet. The error was sitting there, hidden in plain sight, shaping our understanding of not just Jupiter but of all giant planets everywhere. Scientists studying exoplanets, planets circling other stars, used Jupiter as their reference point. When they found a gas giant far away, they'd say it's twice the size of Jupiter, or half the size, or similar to Jupiter. Those comparisons relied on Jupiter's measurements being correct. Models of how planets form, how they evolve, how their atmospheres behave, those models used Jupiter's numbers as input. If Jupiter's size was off, all those models were off too. But the error was small enough, subtle enough, that it didn't create obvious problems. It just sat there, a small imprecision in the baseline data, while we built more and more on top of it. Think about how that happens in your own life. You learn something early on, something that seems true, something everyone agrees on. Maybe it's about health, or money, or relationships. And you build your decisions on that belief. You pass it on to others. It becomes part of how you see the world. Then one day something challenges it. New information arrives. A better way of understanding shows up. And suddenly you realize that thing you were so sure about wasn't quite right. It's unsettling. It shows how knowledge improves over time. But it's also exciting, because it means you're learning, you're growing, you're seeing more clearly than before. That's where we were with Jupiter. We'd learned something that seemed true. We'd built on it for 5 decades, and we had no idea we were about to see more clearly. But that moment was coming. A new spacecraft was being built, one designed specifically to study Jupiter in ways no mission ever had before. It would arrive with instruments so precise, so sophisticated, that they could measure Jupiter down to incredible detail. And when those measurements came back, everything we thought we knew was about to be questioned. Scientists were about to face a choice: trust the old numbers that everyone had accepted for decades, or trust the new numbers that didn't match. And choosing the new numbers meant admitting something uncomfortable, that we'd been teaching the wrong information for half a century, that textbooks around the world needed correcting, that our picture of Jupiter had been blurred this whole time. The mission that would force that choice was already on its way, carrying instruments that would see through the blur and show us what Jupiter really looked like. Its name was Juno, and it was about to change everything. NASA launched Juno in August of 2011. The spacecraft was built for one purpose: to understand Jupiter. Not fly past it like the earlier missions did, not snap a few pictures and keep going, but to arrive, to stay, to orbit, to study Jupiter in depth like never before. The mission was ambitious. Jupiter sits far from the Sun, which meant Juno couldn't rely on solar panels the way spacecraft closer to Earth do. But NASA designed it anyway, giving it enormous solar arrays that would capture what little sunlight reaches Jupiter's neighborhood. The spacecraft was tough, built to survive Jupiter's brutal radiation environment, and it carried instruments designed to peer inside Jupiter's atmosphere, to measure its gravity with incredible precision, to map its magnetic field, to answer questions we'd been asking for decades. The journey took 5 years. Juno travelled over 1 billion miles, looping through space to pick up speed, using Earth's gravity like a slingshot to boost itself toward the outer solar system. Scientists waited. Engineers monitored every system. The public followed along, watching updates, learning about what Juno would do when it arrived. And on the 5th of July in 2016, Juno reached Jupiter. It fired its main engine for 35 minutes, slowing down just enough to let Jupiter's gravity capture it. The spacecraft entered orbit. The mission began. Right from the start, Juno saw things we'd never seen before. It flew closer to Jupiter's cloud tops than any previous spacecraft. It passed over the poles, giving us our first real look at what the top and bottom of Jupiter looked like, and those views were stunning. The poles weren't like the rest of Jupiter. They didn't have neat bands of colour. Instead, they showed massive storms clustered together, swirling chaos, beauty mixed with violence. Scientists stared at the images, realizing how much we'd been missing by only seeing Jupiter's equator and middle latitudes. The poles were different, stranger, more complex than anyone had guessed. But Juno wasn't just taking pictures. Its main job was to measure. It carried an instrument that could track tiny changes in radio signals as the spacecraft orbited. When Juno passed over different parts of Jupiter, the planet's gravity would pull on it slightly differently. Those pulls would change Juno's speed, and those speed changes would show up in the radio signals. By tracking those signals with enormous precision, scientists could map Jupiter's gravity field, and from that gravity field they could calculate exactly how mass was distributed inside Jupiter. They could figure out if Jupiter had a solid core or if it was gas all the way down. They could measure how the planet bulges at the equator and flattens at the poles. They could, for the first time, get precise measurements of Jupiter's exact shape. The data started coming back. Scientists began their analysis, and almost immediately something felt wrong. The numbers didn't match what the Pioneer and Voyager missions had found. At first, the team assumed there was a problem with Juno's instruments. Maybe something got damaged during the journey, or during the intense radiation exposure near Jupiter. They checked everything. They ran diagnostics. The instruments were fine. They were working exactly as designed. So the scientists ran the calculations again. They processed the data a different way. They looked for errors in their models, in their assumptions, in their methods. But the numbers kept coming back the same. Jupiter was smaller at the equator than the old measurements said, and it was more flattened at the poles than anyone had calculated. This wasn't a small difference. This wasn't something you could explain away as a minor correction. The discrepancy was big enough that it couldn't be ignored. Big enough that it meant something fundamental was wrong with the measurements we'd been using for 5 decades. But how could that be? 4 different spacecraft in the 70s had all agreed. Decades of scientific work had been built on those numbers. Could they all have been wrong? The Juno team did what good scientists do when they get unexpected results. They measured again, and again, and again. Each time Juno completed an orbit around Jupiter, it collected more data. Each orbit added more precision, and every time the result was the same. Jupiter was smaller and flatter than we thought. The evidence was overwhelming. But that created a problem. How do you announce to the world that something everyone has believed for half a century turns out to be incorrect? How do you explain that textbooks need to be rewritten, that models need to be updated, that the very foundation of our understanding of Jupiter was built on flawed measurements? The team took their time. They checked everything multiple times. They wrote up their findings carefully, documenting every step, showing their work, making sure there was no room for doubt. They submitted their research to Nature Astronomy, one of the most respected scientific journals in the field. The paper went through peer review, where other scientists examined the work, tested the conclusions, made sure everything was solid. And in early 2026, the paper was published. NASA made the announcement. Jupiter's size had been corrected. The numbers we'd been teaching for 5 decades were wrong. The reaction in the scientific community was a mix of surprise and fascination. Some scientists had suspected something was off. There had been hints over the years, small inconsistencies that didn't quite add up, but nothing definitive enough to challenge the established measurements. Now those hints made sense. Others were surprised. They'd built their entire careers on models that used the old numbers. Now they'd have to go back and adjust. But overwhelmingly, the response was positive. This is how science is supposed to work. You make the best measurements you can with the tools you have. Then better tools come along, and you make better measurements. And if those measurements show your earlier understanding was incomplete, you adjust. You scientists updated their conclusions based on better data. You follow the evidence wherever it leads. But outside the scientific community, the announcement raised a different kind of question. For most people, science feels permanent. We learn facts in school, and we assume those facts are true. The idea that something as basic as the size of Jupiter could be wrong for 5 decades is unsettling. It makes you wonder what else might be wrong. If we couldn't even measure Jupiter correctly, and Jupiter is right here in our own solar system, a planet we've studied for decades, what does that say about our understanding of things much farther away? Things we can't visit with spacecraft? Things we can only observe from Earth? That's a fair question, and it points to something important about how science works. Science improves its understanding as new evidence becomes available. It's about being right for now, with the understanding that now might change when better information arrives. Scientific knowledge isn't a finished cathedral. It's a building under constant renovation. Sometimes you add new rooms, sometimes you discover the foundation needs reinforcing. And sometimes you realize a wall was built slightly crooked, and you have to tear it down and build it again better this time. Juno's measurements weren't just more accurate because the spacecraft had better instruments, though that was part of it. Juno's measurements were better because the mission was designed from the start to do this kind of precise work. The earlier missions flew past Jupiter quickly. They were moving fast, gathering what data they could in the brief time they had near the planet. Juno, on the other hand, orbits Jupiter. It passes close to the planet over and over again, collecting data from multiple angles, multiple positions. That repetition allows for precision the flyby missions could never achieve. It's the difference between trying to measure something while driving past it on the highway versus parking next to it and taking all the time you need to get the measurement exactly right. And the results were clear. Jupiter's equatorial radius, the distance from its centre to its edge at the widest point, was smaller than we thought. And its polar radius, the distance from centre to edge at the top and bottom, was also smaller, but proportionally more so, meaning the planet was flatter than we'd calculated. The degree of flattening, which scientists call ablateness, was greater than the old numbers showed. Jupiter bulges less at the equator and pinches more at the poles than we'd been teaching. Now, you might be thinking this all sounds very technical, very abstract. Why does it matter if Jupiter is a bit smaller or a bit flatter? But here's why it matters. Jupiter's shape tells us about what's inside it. A planet's ablateness depends on how fast it spins, how massive it is, and how its material is distributed from the surface down to the core. If the shape is different than we thought, it means our models of Jupiter's interior need adjusting. And those models affect our understanding of how Jupiter formed, how it evolved, how it interacts with its moons, how its magnetic field works. All of that is connected. Change one piece, and other pieces shift too. Scientists are now going back through decades of research, looking at what needs to be updated. Some things won't change much, but other things, predictions about Jupiter's core, calculations about its gravitational influence on nearby objects, comparisons between Jupiter and similar planets around other stars, those will shift. And that's exciting. That's science doing what it's supposed to do, not clinging to old ideas, but embracing new information and adjusting accordingly. But the question that everyone started asking as soon as the announcement came out was the obvious one. How did we miss this for so long? Let me paint you a picture of what this discovery really means, beyond the numbers and the scientific jargon. Imagine you've had a photograph of someone you love sitting on your shelf for 50 years. You look at it all the time. You know every detail. You could describe it from memory. Then one day, someone hands you a new photograph of that same person, taken at the same age, from the same angle. But this photograph is sharper, clearer, and when you look at it, you realize the person's face was slightly different than you remembered. Not dramatically so. They're still recognizable. But the details you thought you knew so well, they were blurred in that old photograph, and now you're seeing them clearly for the first time. That's what happened with Jupiter. The announcement came in February of 2026. NASA released the findings from Juno's extended mission, findings that had been reviewed, verified, and published in Nature Astronomy. The headline was simple but profound. Jupiter is smaller and more ablate than previous measurements indicated. For anyone who's spent their life learning about the solar system, teaching about it, writing about it, that sentence carried weight. It meant every visualization of Jupiter that showed its size to scale, slightly off. Then every textbook that listed Jupiter's dimensions, slightly wrong. Every comparison between Jupiter and other planets, slightly inaccurate. Not catastrophically so, but enough that it mattered. Here's what Juno found. Jupiter's equatorial radius, the measurement from the planet's centre out to its edge at the widest point around its middle, was smaller than what we'd been using since the 1970s, and its polar radius, from the centre to the top or bottom, was even more reduced. That means the planet is more squashed than we thought. If you could somehow place the old Jupiter and the new Jupiter side by side, you'd see the difference. The new Jupiter looks like someone pressed down on it from above and below, flattening it more than the old version showed. It's still a giant, still the largest planet in our solar system by far. But it's a slightly smaller, slightly flatter giant than we'd been picturing. The term scientists use for this flattening is ablateness. It's a measure of how much a spinning object bulges at its equator compared to its poles. Earth has some ablateness. We're not a perfect sphere either. Our planet spins, and that spin pushes material outward at the equator and pulls it inward at the poles. But Earth spins slowly, one rotation every 24 hours, so the effect is small. Jupiter spins much faster. A full day on Jupiter is less than 10 hours. That rapid rotation creates a strong outward force at the equator, which should make Jupiter bulge significantly, and it does. But not quite as much as the old measurement suggested. Why does this matter? Because a planet's shape is tied directly to what's inside it. If Jupiter were made of the same material all the way through, uniformly dense from surface to core, it would flatten into a specific shape when spinning at its current speed. If it has a dense core surrounded by lighter material, it would flatten differently. The exact degree of flattening tells scientists about the interior structure. It's like feeling the weight of a wrapped gift to guess what's inside. The shape gives you clues, and when the shape changes, even slightly, those clues change too. Scientists have been arguing for years about whether Jupiter has a solid core or not. Some models say yes, there's a dense core of rock and metal at the centre, maybe 10 or 15 times Earth's mass, surrounded by layers of liquid metallic hydrogen, and then the gas we see on the surface. Other models say no, Jupiter is more mixed, and with heavy elements scattered throughout rather than concentrated in a core. Juno's measurements of Jupiter's gravity field and shape are helping to settle that debate, and the corrected size measurements matter for that work. They change the calculations, they shift the models, and slowly, carefully, scientists are building a more accurate picture of what lies beneath Jupiter's clouds. But let's step back from the technical details for a moment and think about what this discovery represents on a human level. We've been looking at Jupiter for thousands of years. Ancient astronomers tracked it across the sky. Renaissance scientists studied it through early telescopes. Space-age engineers sent machines to visit it. And through all of that, we were seeing it slightly wrong. Not completely wrong. We knew it was a giant. We knew it was made mostly of hydrogen and helium. We knew it spun fast and had storms and moons. All of that was correct. But the precise shape, the exact dimensions, those were off. And nobody knew. For half a century, nobody knew. That's humbling. It reminds us that even our best measurements, our most confident conclusions, come with limits. We can only measure as well as our instruments allow. We can only see as clearly as our technology permits. And when better instruments come along, when technology improves, we see things we missed before. Sometimes those things are small details that don't change much, and sometimes they're big enough that we have to rewrite what we teach. This was one of those times. The scientific paper that announced these findings laid everything out carefully. The researchers explained their methods, showed their data, compared the new measurements to the old ones, and calculated the uncertainties. Science works on uncertainty. Every measurement comes with a margin of error, a range within which the true value probably lies. The Pioneer and Voyager measurements had uncertainties too. At the time, those uncertainties seemed small enough that the measurements were considered reliable. But Juno's measurements have much smaller uncertainties. The precision is far better, and when you compare the two sets of measurements, even accounting for the uncertainties, they don't overlap. That's the clear sign that something was wrong with the old numbers. Now, the scientists who worked on the Pioneer and Voyager missions back in the 70s didn't do anything wrong. They used the best techniques available at the time. They analysed their data carefully. They reported their results honestly. The problem wasn't with their work. The problem was with the limits of what was possible back then. The spacecraft were moving quickly past Jupiter. The instruments weren't as sensitive as what we can build today. The radio tracking wasn't as precise. And the models they used to interpret the data were simpler, because computers were less powerful and computational techniques were less sophisticated. All of those factors combined to produce measurements that were good for their time but not good enough by today's standards. Think about photography again. If you took a picture with a camera from the 70s, it might look fine when you print it small or view it on an old television. But if you blow it up large, you start to see the grain, the blur, the lack of detail. That picture was perfectly acceptable for its time, but compared to a modern high-resolution digital image, it looks fuzzy. That's what happened with Jupiter. The old measurements looked fine when that's all we had, but when Juno came along with its high-resolution instruments, we could see details that had been fuzzy before, and those details revealed that the shape we'd been picturing wasn't quite right. The publication in Nature Astronomy wasn't just about correcting numbers, it was about showing the process of science at work. The paper acknowledged the previous measurements. It explained why those measurements were the best available at the time. It didn't criticize the earlier missions or the scientists who worked on them. Instead, it showed how knowledge progresses, how we build on what came before, even when building on it means correcting it. That's not a failure of science. That's a success. That's science working exactly as it should. When the announcement went public, reactions poured in from around the world. Educators started wondering when new textbooks would reflect the corrected measurements. Planetarium directors began updating their presentations. Science writers worked to explain what had changed and why. And the public, people who care about space even if they're not scientists, started asking the big question. If we were wrong about Jupiter's size, what else might we be wrong about? That question isn't cynical. It's not meant to undermine trust in science. It's genuine curiosity. And it's a question scientists ask themselves all the time. Every measurement, every model. Every conclusion comes with the understanding that it's based on current evidence and current tools. Future evidence, future tools, might reveal something different. That doesn't mean we throw up our hands and say we can't know anything. It means we hold our conclusions with appropriate confidence, strong confidence when the evidence is strong, but always with an openness to revision if better evidence arrives. Jupiter's corrected measurements are now the official ones. NASA's databases have been updated. Scientific papers published after 2026 use the new numbers, and slowly, as textbooks get revised and new editions get printed, students around the world will learn Jupiter's size correctly. The old numbers will fade into history, a footnote in the story of how our understanding improved. And that's exactly how it should be. We don't erase the past, we learn from it. We acknowledge that the old measurements were the best we could do at the time, and we move forward with better information, grateful that we have the tools to see more clearly now. But this correction raises an even more fascinating question, one that takes us deeper into the story. Understanding how we got Jupiter's size wrong for 50 years requires us to step back and think about what it takes to measure something you can't touch, something millions of miles away, something so large that it dwarfs anything in our everyday experience. We measure things around us all the time. You can measure a room with a tape measure. You can weigh yourself on a scale. You can time how long it takes to drive somewhere. These measurements are direct. But measuring a planet across the vast distance of space, that's indirect. You can't stretch a tape measure to Jupiter. You have to use physics, mathematics, and whatever signals you can send or receive across that enormous gap. In the 1970s, when Pioneer and Voyager flew past Jupiter, they used the tools available at that time. One of the main methods involved radio signals. As a spacecraft passes behind Jupiter from Earth's perspective, the planet blocks the radio signals between the spacecraft and Earth. By timing exactly when the signals disappear and reappear, scientists can calculate the planet's size. It sounds simple, but it requires knowing the spacecraft's exact position, its exact speed, and accounting for how Jupiter's atmosphere bends radio waves. All of those factors introduce uncertainty. Small errors in any one of them add up. Another method used gravity. As a spacecraft flies near a planet, the planet's gravity pulls on it, changing its speed and direction. By tracking those changes very precisely, you can calculate the planet's mass and how that mass is distributed. But again, this requires extreme precision. You need to know the spacecraft's trajectory perfectly. You need to account for the influence of Jupiter's moons, which also pull on the spacecraft. You need powerful computers to run the calculations, and in the 70s, computers were nowhere near as powerful as they are today. The models were simpler, the calculations took longer, and the results, while impressive for their time, had larger margins of error than what we can achieve now. There's something else that played a role, something more human. Once the Pioneer and Voyager missions reported their measurements, and once those measurements were published and peer-reviewed and accepted by the scientific community, they became the standard. They went into reference books. They became the numbers everyone used. And once something becomes the standard, it takes significant evidence to challenge it. It's not that scientists are stubborn or closed-minded. It's that science rightly demands strong proof before overturning accepted conclusions. If every new measurement was treated as overriding all previous work, science would be chaos. So there's a built-in conservatism, a reasonable resistance to change unless the evidence for change is compelling. For decades after the Voyager missions, no spacecraft visited Jupiter with the specific goal of improving those measurements. Other missions flew by, Ulysses in the 90s, Cassini in the 2000s, but they were focused on other objectives. They took measurements of Jupiter as they passed, but improving the size measurements wasn't their primary mission, and their quick flyby measurements, done with instruments not specifically designed for that purpose, generally agreed with the old numbers within the margins of error. So there was no red flag, no obvious reason to think something was wrong. This is how errors can persist. Not because anyone is doing bad science, but because the error is small enough that it doesn't create obvious contradictions. It fits within the expected range. It doesn't break any models. It just sits there, a small inaccuracy that everyone accepts because it's close enough. And close enough is often sufficient for many purposes. If you're calculating Jupiter's gravitational influence on a comet, The difference between the old measurements and the new ones probably won't change your conclusion significantly. If you're teaching a high school class about the solar system, the old numbers worked fine for giving students a general sense of Jupiter's size. The error mattered most for highly precise work, for scientists trying to understand Jupiter's interior structure in detail, for models that needed exact inputs. And until Juno arrived, we didn't have better numbers to use. Juno changed everything because it was designed specifically for precision. It wasn't flying past Jupiter, it was orbiting, coming back, again and again, measuring from multiple angles, multiple distances. Its instruments were built with decades of technological advancement behind them. The radio tracking system could measure tiny changes in the spacecraft's velocity with extraordinary accuracy. The gravity science experiment could map Jupiter's gravitational field in detail that would have been impossible in the 70s, and the computers processing all this data were millions of times more powerful than what NASA had available during the Voyager era. All of that combined to produce measurements with much smaller uncertainties, much higher confidence. But there's a deeper lesson here, beyond just the technology. Science is a human endeavor. It's done by people, with all the limitations people have. We can only work with the tools we have at any given moment. We can only think within the frameworks we've learned. We can only imagine what our current understanding allows us to imagine, and sometimes we get comfortable with what we think we know. We stop questioning it because it seems settled, and that comfort can make us miss things. The scientists working on Juno could have assumed the old measurements were correct. They could have calibrated their instruments to match the established numbers. They could have dismissed early data that didn't fit as errors in their own work, but they didn't. They trusted their instruments. They trusted their methods. And when the numbers kept coming back different from what was expected, they took that seriously. They investigated. They checked everything multiple times. And when they were confident their measurements were accurate, they reported what they found, even though it meant challenging 5 decades of accepted science. That takes courage. It takes intellectual honesty. And it's exactly what science needs. Think about the parallels in everyday life. How often do we accept something as true because everyone around us accepts it? How often do we stop questioning something because it seems like everyone agrees? And how hard is it to speak up when you notice something doesn't quite fit, something seems off, something might be wrong? It's uncomfortable. It invites skepticism. People might think you're mistaken, but progress, whether in science or in life, requires people willing to question, willing to look closer, willing to say, wait, let me check that again, even when everyone else has moved on. The story of Jupiter's measurements is also a story about how scientific consensus forms and how it changes. Consensus is important. It's how we build shared knowledge. But consensus isn't the same as truth. It's the best understanding we have at the moment based on available evidence. And when new evidence arrives that contradicts consensus, science has a mechanism for handling that. You present your evidence, others examine it, they try to replicate it, they test it against different methods, and if the new evidence holds up, consensus shifts. It might shift slowly, reluctantly, with lots of debate, but it shifts. That's how we got from Earth-centered astronomy to sun-centered astronomy. That's how we got from believing continents were fixed to understanding plate tectonics, and that's how we're getting from the old measurements of Jupiter to the new ones. There's also something worth noting about technology and timing. Juno launched in 2011, but spacecraft like Juno could have been built earlier. The technology was mostly available, so why did it take until 2016 for a spacecraft to reach Jupiter with instruments precise enough to catch this error? Part of the answer is funding. Space missions are expensive. NASA has to prioritize. There are always more mission proposals than there is money to fund them. Juno competed against other missions, other priorities, and it took years of advocacy by scientists to convince NASA that sending an orbiter to Jupiter was worth the investment. If funding had been different, if priorities had been different, we might have discovered this error a decade earlier. Or we might still not know about it. The timing of discovery isn't just about when technology becomes available, it's about when resources, interest and need align. Another factor is the natural pace of space exploration. Missions take years to plan, years to build, years to travel to their destinations. Pioneer reached Jupiter in 1973, Voyager in 1979. Then there was a gap of decades before Galileo arrived in 1995 to orbit Jupiter, but Galileo's mission focused on other science questions, the moons, the magnetosphere, the atmosphere, not on refining the size measurements. Juno was the first mission since Voyager, with the specific goal of understanding Jupiter's interior structure, which required precise measurements of its gravity field and shape. So in some sense, it took this long because we had to build the scientific case for why such a mission was needed, then build the mission itself, then send it on its long journey. Science moves at its own pace, not always as fast as we might like. And there's one more element to consider. Errors in measurement often go unnoticed until you have a strong reason to look for them. If the old measurements of Jupiter had created obvious problems, if models based on those measurements kept failing, if predictions kept being wrong, someone would have investigated sooner. But the measurements were close enough to the truth that models mostly worked. Predictions were mostly accurate, so there was no crisis, no urgent reason to question the numbers. It took a mission designed for extreme precision, looking closely at questions that required that precision to reveal the discrepancy. That's not unusual. Many scientific errors are discovered not because someone sets out to find errors, but because someone is trying to answer a new question and needs better data to do it. And in getting that better data, they stumble onto the error. So how did we get it wrong? We got it wrong because we were working with the best tools available at the time, and those tools had limits. We got it wrong because once measurements are established and accepted, they're hard to challenge without strong evidence. We got it wrong because no one had a strong reason to question the numbers until a mission capable of better measurements arrived. And we got it wrong because that's how science works. You do the best you can with what you have, and you trust that future scientists with better tools will correct your mistakes. It's not a flaw in the process, it's the process itself. And now that we know Jupiter's size more accurately, we have to ask, what does this mean for everything else we think we know? That question opens up a whole new layer to this story. You might be wondering why any of this matters beyond correcting a number in a textbook. Jupiter's a long way away. It doesn't affect your daily life, whether it's slightly bigger or slightly smaller than we thought. And on one level, that's true. But on another level, this discovery ripples outward in ways that touch more than you might expect. Because Jupiter isn't just another planet, it's a key to understanding worlds far beyond our solar system, and it's a reminder that precision matters even when the stakes seem distant and abstract. Let me explain what I mean. When astronomers discover planets around other stars, exoplanets, they can't measure those planets directly. The planets are too far away, too faint, too small compared to their bright parent stars. Instead, astronomers infer the planet's sizes and masses from indirect signals. They watch how much a star's light dims when a planet crosses in front of it. They measure how much a star wobbles due to a planet's gravitational pull. And then they try to figure out what kind of planet would produce those signals. Is it rocky like Earth? Is it a gas giant like Jupiter? Is it something in between? To answer those questions, astronomers compare the exoplanets to planets in our own solar system. Jupiter is the standard for gas giants. When scientists discover a big planet around another star, they describe it in terms of Jupiter. This planet is twice Jupiter's mass, they'll say, or this planet is half Jupiter's size. Those comparisons help us picture what the distant planet might be like. But those comparisons only work if we know Jupiter's mass and size accurately. If our measurements of Jupiter are wrong, then all the comparisons are off too. We're using a flawed ruler to measure everything else. Now that we have corrected measurements of Jupiter, scientists can make better comparisons. They can classify exoplanets more accurately. They can build better models of how gas giants form and evolve. And they can make better predictions about which exoplanets might be worth studying in more detail. That matters because we're living in an era where we're finding thousands of exoplanets, where we're starting to study their atmospheres, where we're searching for signs of life on worlds that might resemble Earth. Getting the fundamentals right, like Jupiter's size, makes all that other work more accurate. There's another reason this matters. Jupiter's shape tells us about its interior, and its interior holds clues to how our entire solar system formed. The current leading theory is that Jupiter formed early, quickly gathering up most of the gas in the disk of material that surrounded the young sun. Once Jupiter got big enough, its gravity influenced everything else. It may have prevented a planet from forming in the asteroid belt. It may have scattered smaller bodies inward, delivering water to Earth. It may have acted like a shield, deflecting comets that might otherwise have bombarded the inner planets. Understanding Jupiter means understanding the environment in which Earth formed, the conditions that allowed life to arise here. And to understand Jupiter, we need to know what's inside it. Does it have a core? If so, how big is that core and what is it made of? How do the different layers transition from one to another? These questions matter because they tell us about the conditions in the early solar system. about how planets grab material from the surrounding disk, about how they evolve over billions of years. Juno's measurements, including the corrected size and shape, feed into models that try to answer these questions. The more accurate the measurements, the more reliable the models. And the more reliable the models, the better we understand not just Jupiter, but the story of how our solar system came to be. But let's bring it closer to home for a moment. Imagine you're building something, a house, a piece of furniture, a machine. And imagine your measuring tape is off by a small amount. Not much, just a little. You measure everything. You cut everything. You build everything based on that tape, and most of it works fine. But here and there, things don't quite fit. Joints aren't as tight as they should be. Pieces don't line up perfectly. Nothing catastrophic. Just small issues that accumulate. That's what happens when foundational measurements are slightly wrong. Most things still work, but precision suffers. And in science, precision matters. It matters because small differences in input can lead to big differences in output when you're running complex models. It matters because we're trying to understand systems that operate on scales and timescales far beyond human experience. And it matters because getting things right is how we build knowledge that lasts. There's also an educational dimension to this discovery. Think about all the students who learned about Jupiter over the past 5 decades. Millions of students, hundreds of millions maybe. They learned numbers that were slightly wrong. Their textbooks showed diagrams that were slightly inaccurate. Does that mean their education was wasted? Not at all. They learned the process of science. They learned about the solar system's structure. They learned to appreciate the scale and beauty of Jupiter. The specific numbers were less important than the larger understanding. But moving forward, students will learn more accurate numbers. They'll see diagrams that reflect Jupiter's true shape more precisely. And maybe, if their teachers are thoughtful, they'll also learn the story of how those numbers were corrected. They'll learn that science isn't about memorizing fixed facts. It's about building understanding that improves over time, and that's a valuable lesson, maybe more valuable than any specific number. This discovery also reminds us of something we often forget in our daily lives. Certainty is rarer than we think. We treat so many things as settled, as known, as beyond question. And most of the time, that's fine. It's practical. We can't question everything constantly. But every once in a while, it's worth remembering that even things that seem certain, things that everyone agrees on, things that have been taught for generations, might turn out to be slightly off. Not because anyone lied or made careless mistakes, but because knowledge is built layer by layer, and sometimes we have to go back and adjust the earlier layers when we learn something new. There's a humility in that. A recognition that we're always working with incomplete information, always seeing through instruments that have limits, always thinking with minds shaped by our time and place. And that humility is healthy. It keeps us open to new information. It keeps us willing to revise our understanding. It keeps us curious. Because if we can be wrong about something as straightforward as the size of a planet we've studied for decades, imagine what else we might be missing. Not in a fearful way, but in an exciting way. What other discoveries are waiting just beyond the limits of our current tools? What else will we learn when the next generation of instruments comes online? Jupiter's corrected measurements are already being used in new research. Papers published after 2026 reference the updated numbers. Models are being revised. Comparisons to exoplanets are being recalculated, and slowly the scientific literature is shifting to reflect our improved understanding. That's how knowledge progresses, not in sudden revolutions usually, but in steady refinement. Most of the time, new discoveries don't overturn everything we thought we knew. They adjust it, they add detail, they correct small errors, and those small corrections accumulate over time into a much clearer, much more accurate picture of reality. So why does Jupiter's corrected size matter? It matters because precision in science has downstream effects. It matters because Jupiter is our reference point for understanding gas giants everywhere. It matters because getting the fundamentals right makes everything we build on those fundamentals more reliable. And it matters because it reminds us that knowledge is never truly finished. There's always more to learn, always more to discover, always room for improvement. And that's not a weakness. That's science's greatest strength. It's why we trust science even though it sometimes corrects itself. Because that self-correction is how we get closer and closer to truth. And truth, even about something as distant as Jupiter, is worth pursuing. But this realization about Jupiter naturally leads us to wonder, what else might be waiting to be corrected? The question sitting in the back of your mind right now is probably the same one that popped up in mine when I first learned about this discovery. If we were wrong about Jupiter for half a century, what else have we gotten wrong? It's a fair question, maybe even an obvious one. And it's a question that makes some people uncomfortable because it seems to undermine the authority of science. But actually, it's exactly the question scientists themselves ask all the time, and the answer is both unsettling and exciting. Let's start with what we know is probably accurate. The basics of the solar system, the order of the planets, their general sizes relative to each other, the fact that they orbit the Sun, those are solid. We've confirmed them through multiple methods, multiple missions, centuries of observations. You don't need to worry that we're suddenly going to discover Earth is bigger than Jupiter, or that Mars is actually closer to the Sun than Venus. The fundamentals are sound. But the details, the precise measurements, those are always subject to revision when better instruments come along. Take Mars, for example. We've sent numerous missions to Mars, orbiters, landers, rovers. We've mapped its surface in extraordinary detail. We know its size much better than we knew Jupiter's size before Juno. But even Mars probably has measurements that will be refined in the future. Maybe its exact mass, which depends on precisely mapping its gravitational field. Maybe the depth of its core, which we're still investigating. Maybe the amount of water ice hidden beneath its surface. These aren't wild uncertainties. We have good estimates, but good estimates are not the same as perfectly accurate measurements. And as technology improves, our estimates will get better. Or consider the outer planets, Uranus and Neptune. We've only visited them once briefly with Voyager 2 back in the 1980s. Everything we know about their sizes, their masses, their internal structures comes largely from that one flyby mission. The measurements are the best we could get at the time, but they're based on old technology and brief observations. If we sent a modern orbiter to Uranus or Neptune, equipped with instruments like Juno's, would we find surprises? Almost certainly. Would we discover their sizes are wrong too? Maybe. We won't know until we go back and look more carefully, and right now, there are no firm plans to return to either planet anytime soon. Then there are measurements beyond our solar system, distances to stars, sizes of stars, ages of galaxies. These are calculated using chains of inference, methods built on methods built on methods, and each step in the chain has uncertainties. Small uncertainties in early steps can compound into larger uncertainties in later steps. Astronomers are aware of this. They work constantly to refine their measurements, to find new ways to check their results, to reduce uncertainties, but the work is never finished. There's always room for improvement. Now, I want to be clear about something. Asking what else might be wrong is not the same as saying we can't trust science. It's recognizing that science is a process, not a finished product. Scientific knowledge is our best current understanding, with the understanding that current is doing a lot of work in that sentence. When we teach scientific facts, we're teaching what we know right now, based on evidence gathered up to this point. And most of those facts are rock solid. But some of them, usually the very precise measurements, the ones that push the limits of what we can observe, those are more provisional. They're likely to be refined as technology improves. Think of it like maps. Old maps of the world were mostly right. They showed continents in roughly the right places. They showed the general layout of coastlines, but the details were off. Coastlines were simplified. Distances were approximate, small islands were missing or misplaced. As surveying technology improved, maps got more accurate. The continents didn't move, but the maps representing them got closer and closer to reality. That's what's happening with our understanding of the universe. The big picture is correct, but we're constantly improving the details, making the map more precise, filling in gaps we didn't know were there. So what specific things might be wrong? Honestly, it's hard to predict. That's part of what makes science exciting. If we knew what was wrong, we'd fix it. Discoveries come when we look more carefully at something we thought we understood and find a surprise. Jupiter's size was a surprise because nobody expected it to be wrong. The measurements seemed good. They'd been used for decades without problems. It took a mission designed for unprecedented precision to reveal the error, and there are probably other measurements like that, sitting in our databases, accepted as correct, waiting for someone with better instruments to check them again. Here's what we can say with confidence, though. The process of science is designed to catch these errors eventually. Science isn't one person making a measurement, and everyone else accepting it forever. Science is a community of people checking each other's work, repeating measurements, testing conclusions, building new instruments to look more closely. And when errors are found, the system corrects them. Not always quickly, not always easily, but reliably. That's why scientific knowledge, even though it sometimes gets corrected, is still the most reliable form of knowledge we have, because it has self-correction built into the process. There's something else worth thinking about. Some things might not be wrong so much as incomplete. Take dark matter, for example. Scientists know that the gravity we observe in galaxies is stronger than what the visible matter can account for, so there's either matter we can't see, or our understanding of gravity is incomplete. We call the missing stuff dark matter, but we don't know what it is. Is our current model wrong? Not exactly. It's incomplete. We're missing a piece of the puzzle. And until we find that piece, our understanding will have a gap. But that gap doesn't mean everything else is wrong. It means there's more to learn, or take the measurements of the universe's expansion rate. Different methods give slightly different results. Not hugely different, but enough that it's noticeable. Does that mean one method is wrong? Maybe. Or maybe there's something subtle we're not accounting for, some factor that affects one method differently than the other. Scientists are investigating, they're checking their work, they're looking for where the discrepancy comes from, and eventually they'll figure it out. That's how the process works. You find an inconsistency, you investigate, you refine your understanding. I think the important thing to take away from all this is balance. We shouldn't be so skeptical of science that we dismiss every finding as potentially wrong. The vast majority of scientific knowledge is accurate, tested, reliable, but we also shouldn't be so trusting that we forget science is always open to revision. The best attitude is informed confidence, trusting the process, trusting the evidence, but staying open to the possibility that better evidence might change our understanding. That's not weakness. That's intellectual honesty. And here's the exciting part. Every time we discover something that needs correcting, every time we refine a measurement or update a model, we're getting closer to the truth. Knowledge isn't static. It's growing, deepening, becoming more accurate. The fact that we can correct Jupiter's measurements after 50 years isn't a failure. It's a success. It shows that science works, that we're capable of catching our mistakes, that we're not stuck with old errors forever. And that means we can be confident that even if some of what we currently believe turns out to need adjustment, the process will catch it eventually. We'll look more closely, we'll measure more carefully, we'll figure it out. And when we do, our understanding will be richer, more complete, more accurate than before. That's the beauty of this whole enterprise. But beyond the specific details, there's a deeper lesson here, one worth reflecting on. If you step back from the specifics of Jupiter's measurements, from the technical details of spacecraft and instruments, what you find is a story about knowledge itself, about how we come to know things, about how certain we can be of what we know, about the relationship between truth and our understanding of truth. And that story, I think, has something valuable to teach us that goes beyond astronomy. We live in a time when people are questioning everything, and I mean everything. Trust in institutions is declining. People are skeptical of experts. Facts themselves seem to be up for debate. And in that environment, a story like this, where scientists discover that something they taught as fact for 5 decades was wrong, can feel like it confirms that skepticism. See? Even the experts don't know what they're talking about. Even science gets things wrong, so why should I trust anything? But that's exactly the wrong lesson to take from this. The right lesson is almost the opposite. Science got Jupiter's measurements wrong for 5 decades, yes. But science also corrected itself. It didn't take some outsider pointing out the error. It didn't take a conspiracy being revealed. It took scientists building better instruments, making more careful measurements, trusting their new data even when it contradicted the old consensus, and reporting their findings honestly. That's the system working exactly as it should. Compare that to other ways of knowing things. If a religious text says something, and new evidence suggests it's not quite right, can the text be revised? Usually not. Religious truth claims tend to be treated as permanent. If a political ideology makes a prediction that doesn't come true, do believers abandon the ideology? Rarely. They usually find ways to explain away the failure. But science? Science is designed from the ground up to change its mind when evidence demands it. That's not a bug. That's the feature that makes science powerful. The key is understanding what scientific knowledge actually is. It's not a collection of eternal truths handed down from on high. It's a continuously updated model of reality, built from observations and experiments, tested against new evidence, revised when necessary. Scientific facts are better thought of as well, supported conclusions that we hold provisionally, always open to revision, if better evidence comes along. That sounds less certain than facts, and in a way it is. But it's also more honest. It's acknowledging the reality of how knowledge works. Think about your own life. How much of what you believed 20 years ago have you revised? Not the core values maybe, but the specifics. How you think about relationships, how you manage your health, how you understand the world. You've learned things. You've had experiences that changed your perspective. You've discovered that some things you were sure about turned out to be more complicated than you thought. Does that mean you were stupid or wrong to believe those things back then? No. It means you were working with the information you had, and you've since gained more information. That's growth. That's wisdom. That's exactly what science does on a collective level. The problem comes when we confuse confidence with certainty. Science is confident in its conclusions when the evidence is strong, and that confidence is justified. But confidence doesn't mean the conclusion can never be revised. It means the conclusion is reliable enough to build on, to use, to teach. Jupiter's old measurements were reliable enough for most purposes. They served us well for 50 years. They weren't perfect, but they were good enough. And when we developed tools to measure more precisely, we improved them. That's not a failure, that's progress. Here's another angle on this. Science is done by humans. Humans who are brilliant and dedicated, yes, but also humans who are limited by their time, their tools, their imaginations. The scientists of the 1970s were not less intelligent than scientists today. They were working with less powerful instruments, less advanced computing, less accumulated knowledge. They did remarkable work with what they had, and scientists today are doing remarkable work with what we have. But a century from now, scientists will look back at our work and see its limitations too. They'll have tools we can't imagine. They'll see things we're missing. And they'll refine what we've figured out, just like we're refining what previous generations figured out. That's the cycle. That's how knowledge grows. Not through one generation getting it all right and everyone after just memorizing their conclusions, but through each generation building on what came before, adding new observations, correcting errors, pushing the boundaries a little further. It's cumulative, it's collaborative across time, and it's beautiful if you think about it that way. We're all part of a long conversation that stretches back centuries and will continue long after we're gone. The conversation never ends. The questions keep evolving. The answers keep getting better. Now, does this mean we should be skeptical of everything science tells us? Should we assume every fact might be wrong? No. That way lies paralysis. You can't function if you question everything constantly. What it means is we should hold our beliefs with appropriate firmness. Strong evidence deserves strong confidence. Weak evidence deserves caution, and we should stay open to revision when new evidence arrives. That's not wishy-washy relativism. That's rational thinking. In your own life, you probably do this already without thinking about it. You trust your doctor's advice because it's based on medical evidence, but if new research suggests a different approach, you're willing to adjust. You follow a recipe because it's been tested, but if you try it and it doesn't work, you modify it. You believe what trustworthy sources tell you, but you're not shocked if details turn out to be more complicated than the initial report. That's exactly the attitude that makes sense with scientific knowledge too. The story of Jupiter's measurements also teaches something about intellectual humility. The smartest, most accomplished scientists in the world were teaching numbers that turned out to be wrong, not because they were careless or dishonest, but because they were human, working with imperfect tools. And when that error was discovered, the response wasn't defensiveness or denial. It was curiosity. It was investigation. It was acceptance of the new evidence and adjustment of the old conclusions. That's the kind of humility we could use more of in all areas of life. The willingness to say, I was wrong, or I didn't know that, or let me reconsider. That's strength, not weakness. And finally, this story is a reminder that the universe doesn't care what we believe about it. Jupiter is the size it is, regardless of what our textbooks say. Reality exists independent of our models of it. Our job is to make our models match reality as closely as possible, and we do that by observing carefully, measuring precisely, thinking critically, and always being willing to update our models when reality tells us we're off. That's the contract science makes with truth. We'll do our best to understand you, and we'll admit when our understanding falls short. So what's the bigger lesson? It's that knowledge is a journey, not a destination. It's that certainty is rare and usually overstated. It's that the willingness to change your mind in light of new evidence is a virtue, not a vice. And it's that the process matters more than any single conclusion. The process of science, observe, hypothesize, test, revise, repeat, is what makes scientific knowledge trustworthy, even when specific facts get corrected, because the process keeps working, keeps refining, keeps moving us closer to truth. And that's something worth appreciating, worth defending, worth participating in. These reflections bring us naturally to a place where we can wrap this journey together and look ahead. So here we are at the end of a journey that started with a simple but startling fact. Jupiter is smaller and more flattened than we thought, and we've been teaching the wrong numbers for half a century. We've walked through how that happened, why it took so long to discover, what it means for our understanding of the solar system and beyond, and what it teaches us about the nature of knowledge itself. It's been quite a journey, and I hope you found it as fascinating as I have. But before we part ways, let me bring all these threads together and leave you with some thoughts about where we go from here. Jupiter hasn't changed. It's been spinning in the same orbit, holding the same shape for billions of years. What changed was our ability to see it clearly. The Juno spacecraft, with its advanced instruments and its carefully designed orbit, gave us eyes sharp enough to measure Jupiter more precisely than ever before, and those measurements revealed that our previous understanding, while close, wasn't quite right. The planet is smaller at its equator and more squashed at its poles than the measurements from the 1970s indicated. It's not a dramatic difference, but it's significant enough to matter for scientists trying to understand Jupiter's interior, for astronomers comparing Jupiter to planets around other stars, for educators teaching the next generation about our solar system. The discovery happened because scientists were willing to trust their data even when it contradicted decades of accepted knowledge. The Juno team could have assumed their instruments were wrong. They could have adjusted their results to match the old numbers, but they didn't. They checked their work carefully, confirmed that their measurements were accurate, and reported what they found. And the scientific community, for its part, didn't reject the new measurements out of hand. Scientists examined the evidence, looked at the methods, compared the old data to the new data, and accepted that a correction was needed. That's science working as it should, not clinging to old ideas but following the evidence wherever it leads. This correction ripples outward. Textbooks will be updated slowly but steadily, so future students learn Jupiter's size correctly. Scientific models will be revised to use the new measurements, making predictions about planetary formation and evolution more accurate. Comparisons to exoplanets will be recalculated, helping us better understand the diversity of worlds beyond our solar system. And all of that makes our picture of the universe a little clearer, a little more precise, a little closer to truth. But beyond the specific facts about Jupiter, this story offers something deeper. It reminds us that knowledge is always provisional, always open to revision when better evidence arrives. That's not a weakness of science, it's its greatest strength, because it means we're not stuck with our mistakes forever. We can correct them, we can improve, we can see more clearly as our tools get better and our understanding deepens, and that process never stops. Even the measurements Juno has given us, as precise as they are, will probably be refined someday when even better instruments come along, and that's okay. That's how progress works. The question that naturally arose from this discovery, what else might we have wrong, is a good question, one worth asking. Not in a cynical way, not to undermine trust in science, but in a curious way. What other measurements are we making at the limits of our current technology that future instruments will refine? What other assumptions are we holding that better data might challenge? We don't know until we look more carefully, and that's exciting. That's what drives exploration, what motivates missions like Juno, what keeps scientists pushing to build better instruments and ask deeper questions. I hope this story has given you a new appreciation for how science works, not as a collection of fixed facts to memorize, but as a living, growing, self-correcting process. A process that acknowledges its own limitations, that builds in mechanisms for catching and correcting errors, that values truth over ego. And I hope it's reminded you that the willingness to change your mind when presented with better evidence is something to admire, not something to criticize. Whether in science or in life, being open to new information, being willing to say I was wrong, being humble enough to update your understanding, those are signs of wisdom, not weakness. Jupiter itself, that giant banded world with its swirling storms and orbiting moons, continues on as it always has, indifferent to our measurements, unbothered by our textbooks, simply existing in all its massive glory. But our understanding of it has sharpened. Our picture of it has come into better focus. And that matters because Jupiter is part of the story of where we come from, part of the environment that shaped Earth, part of the context in which life arose on this small blue world. Understanding Jupiter means understanding ourselves a little better, understanding our place in this solar system, in this universe. And Juno's work isn't finished. The spacecraft continues to orbit Jupiter. HASA continues to gather data, continues to reveal new insights. There are more discoveries coming, more surprises waiting. Maybe other measurements that will need correcting, maybe entirely new phenomena we didn't know to look for. The mission has already exceeded its planned duration, and as long as the spacecraft keeps functioning, it will keep teaching us. That's the nature of exploration. You go looking for answers to specific questions, and along the way, you find things you weren't expecting. That's when science gets really interesting. So where does this leave us? It leaves us with a corrected measurement, yes, but more importantly, it leaves us with a reminder of why curiosity matters, why precision matters, why humility matters. It leaves us with appreciation for the scientists who do this painstaking work, measuring planets millions of miles away, running calculations, checking results, reporting findings honestly even when those findings challenge what everyone thought they knew. And it leaves us with wonder at the fact that we tiny humans on this tiny planet can reach out across the vast darkness of space and measure the shape of a giant world. Wonder at how far we've come in our understanding, and how much farther we still have to go. If this journey through Jupiter's corrected measurements has sparked something in you, curiosity about what else is out there, appreciation for how science works, wonder at the universe we're part of, then I've done what I set out to do. And if you want to continue exploring these kinds of stories with me, stories about discovery and correction and the ongoing quest to understand our universe, I'd be honored if you'd subscribe. There's so much more to explore together. Hit that subscribe button and you'll join a community of people who find joy in learning, who appreciate the process of discovery, who understand that knowledge is a journey we're all on together. And I'm genuinely curious. Drop a comment and tell me what you think we might discover next. What other measurements might be refined? What other surprises might be waiting in our solar system? What would you most want to explore if you could send a spacecraft anywhere? I read every comment, and your thoughts always add something valuable to these conversations. You're not just watching these videos, you're part of a community of curious minds thinking together about our place in the universe. Thank you for spending this time with me, for following this story from the initial shock of discovery through the investigation of how it happened to the deeper questions about what it all means. Thank you for your curiosity, your attention, your willingness to think carefully about how we know what we know. The universe is vast and full of mysteries, and we're all explorers together, trying to understand it one discovery at a time. Jupiter just got smaller, yes, but in a way, the universe just got bigger, because we're seeing it more clearly than we ever have before, and that's something worth celebrating. Keep looking up, keep asking questions, keep learning, because the next discovery is always just around the corner, waiting for someone curious enough to look for it.